Okay, welcome to the heat and heat transfer notes review. This is also it's going to be a quick overview of the temperature notes, which I did separate in class, but I'll combine them here. So let's go ahead and start. Are heat and temperature the same thing? No, we definitely differentiate between heat and temperature. They are different things. Heat is the transfer of energy between objects. We'll speak a little bit more about this, but temperature is just basically a way to measure the average amount of energy. Temperature used, obviously we use a thermometer to measure it. It is the energy of the particles of a substance at an immediate, at any one time. For instance, a cup of water can be 100 degrees. That will be the kinetic energy of that amount of water. If you say 8 ounces is the cup of water. However, the thermal energy is different in that it's the total energy of the particles in a substance. For instance, the 8-ounce cup of coffee or 8-ounce cup of tea that is really hot, like 150 degrees, that has a high temperature, but it doesn't necessarily mean it has a lot of thermal energy, because there's not a lot of particles in this small cup of coffee. It's only 8 ounces of water. It's not a lot of molecules of water there. So for instance, an iceberg, which seems to us very cold temperature wise, an iceberg has more thermal energy because it has more particles. Icebergs are huge. They're bigger than ships. So because it has more particles, it has more total energy. Even though they might be moving at a slower rate as our solid up here, it has more of them. So even though they're moving at a slower rate, when you have a lot of them moving at a slow rate, it still adds up to be more thermal energy than the cup of 8-ounce coffee that's 150 degrees. So temperature is just like a measure of the particles of a substance. But thermal energy really has to do with quantity, like how many particles there are. If you remember in the Bill Nye video, he tries to compare the ice sculpture versus the match and which one has more thermal energy. And the ice sculpture most certainly has more thermal energy, and he explains it very well in that all the molecules in the match can burn, and they might be hot at that 1 second, but there's not a lot of particles in the match, so the match will never burn all of the ice sculpture. So I think it's a good comparison. You can check out the Bill Nye video, Heat. There's a link on Edmodo. Go check that out again. That will also be kind of a helpful review. He really kind of hits home that temperature versus thermal energy thing, I think. So how does heat behave? You know this. It's just one of those things that you've always known, but now you understand a little more scientifically. Always transfers from high temperatures to low temperatures. Transfers this way until both objects are the same temperature, equilibrium. If you'll remember the transmitting heat lab that we did with the 2 Ziploc bags, we had the warm water and the cold water. And what happens when you overlap them? Well, they try to reach the same temperature. The cold gets warmer and the warm gets colder, right? Well, that's because the thermal energy from the warm bag, or the heat from the warm bag, transfers over to the cool bag until they reach an equilibrium. Now, they didn't quite reach equilibrium in our lab because we only took data for 15 minutes. But if you look at your graph and if you remember back to it, it would have eventually went to equal, right? So here you see the heat from the hand is flowing into the ice cube. It's making the ice cube melt. The hand is much warmer than the ice cube. And as heat leaves the hand to go into the ice cube, your hand feels what you know of as cold. Really, there's really no cold. It's just an absence of heat. So as heat leaves, you get colder. It's kind of a weird thing. We'll skip over the pop quiz. Thermal expansion. If you remember this, we talked about this. As hot things heat up, they expand. Remember I did this little demo in the class as a lab. I heated it up and then it wouldn't go through, and then as I cooled it down it went straight through the hoop. That is a very good example of thermal expansion, or basically objects spreading out, the particles spreading out and moving more quickly as they heat up. Thermal expansion joints on a bridge are created now because we don't want this over here to happen again. Another good thing to think about with thermal expansion is a thermometer. A thermometer expands and contracts based on this principle of thermal expansion, which I think is one of those things that, you know, again, we understand how they work, but how does it work? Well, it just works because the alcohol or the mercury in the thermometer expands or contracts based on the temperature of the substance that you're putting it in. So, again, this is inverse to expanding. When objects cool off, particles slow down and move inward. The object contracts. Again, if you think back to particles or states of matter, this is something you're very familiar with, right? Here they're more closely together. Here they're more spread apart and moving faster, right? That's exactly what we've been talking about with states of matter. So this kind of is just a carryover from what we've been doing. So expand and contract, this idea is known as thermal expansion. Or thermal contraction, but really thermal contraction is just a part of thermal expansion. It just goes in the opposite way. Again, if I'm going too fast, you know, feel free to rewind the video, pause the video. I'll rewind, or I've already said rewind it, or watch it again. It certainly isn't going to hurt you to watch it again. Heat transfer in 3 ways: conduction, convection, radiation. This is like the wonder diagram because it shows all 3 of them. Conduction here, heat transfer through the through atomic contact. The atoms here are getting really hot, so then the atoms next to it get really hot, and the atoms next to it get really hot, and the atoms get next to it get really hot, and then your hand gets hot because the heat is kind of spread up here from atom to atom. They kinetically start bouncing more and more and more, and that's what heat is. Convection is heat transfer in a liquid, or not necessarily a liquid, I'm sorry, a fluid. And remember, gas is a fluid because air flows. If you ever put your hand outside the car window, you know this. Radiation is heat from a direct source in straight lines. This is why if you stand over here, you get warm from the fire, but your back will not get warm from the fire because radiation is hitting you in a straight shot. So, let's go ahead and carry on. Again, you have conduction, something we all know about. Surely the baby doesn't want to get hurt here, but if he touches this, which is hot, yes, it is going to hurt the baby. There's no doubt about it. Because it's transfer of thermal energy or heat by direct contact, by touching. Right, here's the pot of black beans. If you touch the big metal spoon in it, you're most certainly going to get burned via conduction, because metal's a good conductor. If you remember back to metals being conductors and plastics and rubbers being insulators. Holding an ice cube, as we saw earlier in the video, that is heat transfer via conduction. It's conducting from your hand to the ice cube. So just another example. So we have convection. Convection, transfer of heat, thermal energy by movement of fluids. This is kind of confusing because everybody assumes that fluids are water or liquids, and that's not necessarily the case. Most certainly gases. That's how your air conditioner works in your house. Hot air rises, cold air sinks, and it just kind of follows this little circular pattern like so. It's not exactly a circle, as I'm sure you can imagine, but it's just in this general movement, in this general motion, I would say. And I always think this is a good example because it's something you know, right? Plate tectonics. Plate tectonics move because of convection within the mantle. Magma is at different temperatures. So there's hotter magma closer to the core, and there's cooler magma close to the crust. And this magma, because it's liquidy or a fluid, it will convect. This is what pulls the plates apart. So I always think that's a good example. Boiling water, of course, perfect example. And the last one is radiation. And radiation is transfer of heat or thermal energy by waves without a medium. Remember I was saying in the fireplace, you're sitting here, you get warm on this side, but you don't on the back side because it transfers in direct line. So heat from a fire is the perfect example of radiation. Heat from your heater, if you have like a plug-in heater, that's another good example. So the sun radiates energy. And you'll actually notice here it has a convection zone. I don't really want to get into the physics of the sun, but the sun is very, 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 very large. But it radiates energy out from the core, and then as it radiates it out from the core, then it gets to this certain section, and the fluids actually will, just like the magma in the core of the planet, it actually has hotter sections of magma and cooler sections of magma. Good Lord, seriously? Wireless network? Come on. Oh my gosh. Anyway. Trying to think what else would be good. Good example of that, of radiation. Heat from your stove, you walk up to it, you know it's hot because it's radiating. So anyway, I actually am going to stop the notes here and make a separate video for temperature. I thought I could wrap it all up into one, but YouTube only allows 15 minutes. So I'm at a little bit over 11 now, so I don't think I'm going to make it, and I don't really want to rush it. 3 main heat transfer methods: conduction by touching, convection in a fluid or a gas, or any kind of fluid, which is a gas or liquid, and radiation, which is heat from a direct source and straight lines. Something that's really hot, like a fire. Please kind of revisit this. Don't forget about thermal expansion, thermal contraction. Those are very key things that, they're very simple. This goes right back to states of matter. Object gets hotter, the particles or the molecules, if you want to think about in that sense, spread out and move faster, right? And inversely, as they get cooler, they will contract and get tighter and and the particles move slower. And I think that's good enough. I think I've kind of hit it home. So anyway, hope you enjoyed the video. Check it out again if you need to review or anything like that, and I'll see you in class. Also, I'm sorry, watch the temperature video. It's the next video. You need to watch both of them.